Today's video, we're going to build on what we've done in the past few videos where we use the position representation to sort of look at what the bound states were for a given potential. Today, we're going to look at the first example of unbound states where that energy is larger than the potential. So it's still in a classically allowed region. And we're going to look at essentially the free particle potential. So to recap where we are, we have developed this sort of position representation, which we have this sort of continuous basis representation of position, where our state vector is represented by this wave function. And we have this sort of notation where before our inner product gets evaluated as this integral from negative infinity to positive infinity of the wave function and the complex conjugate of the wave function of those two states, integrated over all the positions. We use this sort of representation to solve the energy eigenvalue equation. Remember, we were trying to figure out what are these actual eigenenergies and what are these eigenenergy functions, because that's what's going to go into our time dependence uh, from our old Dirac notation. If you recall, our time dependence sort of the way we went about this was we would expand the state function in terms of the energy eigenbases and then add those phase factors that depended on the energy eigenvalues, and that would give us our time-dependent state function. In order to get those energy eigenvalues and energy eigenfunctions, we needed to solve this equation, which in the position representation is this, where we have the momentum operator and the position operator. Writing those operators in that position representation gave us this, and that was the differential equation we had to solve to get those energy eigenfunctions and energy eigenvalues. We looked at bound states, the infinite square well and the finite square well, and then just sort of generally how to numerically solve and qualitatively see what those functions would look like but we look specifically at cases where the eigenvalues were less than the potential as a function of position. So in our finite square well, we found those energy eigenvalues that were lower than that potential V naught. Today, we're going to look at unbound states, the states where the energies are greater than the potential and therefore not in those bounded cases. The simplest case is going to be the free particle, where the potential is zero everywhere. So essentially, this is a particle that's, there's no potential attracting it to anywhere in space. It's just free to move wherever. If we do that, our energy eigenvalue equation becomes this. And if we take all of these constants, the h bar and the m, over to the right-hand side, we get sort of a familiar form of our differential equation that we've seen several times before. If we rewrite it this way, second derivative of our energy eigen function is equal to negative some constant, the wave vector squared, times that energy eigenfunction, with that wave vector being equal to 2m en, all square rooted over h bar. We're familiar with this. The one difference in this, this is the same form of the differential equation we saw inside those wells, inside that infinite potential well and the finite well. But the difference is we don't have those boundary conditions we did in those cases, right? There's no, in the infinite well, we had to have that wave function go to zero at the end. And in the finite well, it had to be continuous at the boundary. Here, we don't have those boundaries. We don't have those boundary conditions. Those are what gave us that sort of quantization condition on our wave our wave vector. So we don't have quantization of energy in this case. We actually have a continuous set of energies that will show up as we'll see. But anyway, back to the solutions of what are these energy eigenfunctions. We know from previous lectures and previous courses that we can solve this differential equation using sines and cosines or exponentials. If we write it in terms of exponentials, we get this. The general solution to this differential equation is a e to the ikx plus b e to the minus ikx. And you can see that just you take the derivative, an ik and a negative ik come down in front, do it again, and we get negative k squared times that function. So it does solve that differential equation. Um, so we have a general form sort of our energy eigenfunctions. If we then take that and look at what is the time dependence of a free particle, we're going to do what we did before, right? So we have our function can be written in terms, a general function, state function can be expanded in terms of those energy eigenfunctions with some coefficient, whatever it was at t equals 0. And then we add this time dependent term here, this time dependent phase that has the energy of that eigenfunction in that linear expansion in it. If we do that in this case and just look at, for a given point, a given term in this expansion, we're just going to have the eigenfunction times that energy dependent phase factor here out front. If we take the energy divided by h bar, we get an angular frequency. So we can just rewrite that as an omega here. But this is what we kind of get for that time-dependent sort of coefficient of our linear expansion. We can bring in that the omega and the I into these brackets and then factor out the k. And this is what we end up getting. A ikx minus omega over kt, e to the I minus ikx plus omega over k times t. And you can hopefully realize that these are actually waves in the sense of how we think of classical waves, right? Where you have some function with a shape and the time dependence is just shifting that function. So if you look at the argument here, in this exponent, we have x, and then the time dependence is just adding something or subtracting something from that x variable. So it's shifting it left or right, right? So if, let's just say we have some function at t equals 0, and if we shift it, just shift the argument by negative vt, we shift it to the right. If we shift it by negative vt, we shift it to the left. So, and this is for an arbitrary function of x. If we just replace that x with x plus or minus vt, we get waves traveling to the left or the right. So what we see, our energy eigenfunctions are made up of two terms: a wave moving to the right when it's minus, and a wave moving to the left. So when we think about this, if we go back and just look at the spatial dependence of our energy eigenfunction, we can, instead of writing a e to the ikx plus b e to the negative ikx, we can just write that spatial dependence of our energy eigenfunction as a e to the ikx, but let k be both positive and negative, as opposed to just 0 to infinity here. It goes from negative infinity to infinity here. And that gives us our energy, the form of our energy eigenfunction we're going to use. It's a traveling wave to the left or the right, depending on the sign of that k. If k is negative, we're moving to the left. If it's positive, we're moving to the right in the x direction. So now let's look at some other operators, right? So we have our energy eigenfunctions are equal to a e to the ikx. K can be positive or negative. What about momentum operating on that energy eigenfunction? And you'll see why we're interested in this in a minute. But in the position representation we're using, this momentum operator is just negative I h bar, the derivative with respect to position. And if we operate on that energy eigenfunction with this, well, we can all take derivatives. So we bring that ik down. The negative I times I gives us plus just 1. So we have h bar k times a e to the ikx, or h bar k times that energy eigenfunction. What that means is this is an eigenvalue equation. That operator acting on that function gives us some constant out front. We'll call it p, the momentum, h bar k, times that function, right? So this means we can write the momentum eigenfunctions as the same thing. We'll substitute, we'll write them in terms of p instead of k, and as p, replace k with p over h bar. But they're the exact same function as the energy eigenfunction. The energy and momentum operators in this case share eigenstates. So that means they commute with each other. They are compatible observables in this case. Um, Another thing about that momentum eigenvalue, right? We have this momentum is equal to h bar k, or rewritten in terms for k is equal to that momentum eigenvalue divided by h bar. K is also a wave vector. So we know that that relates to a wavelength as 2 pi over lambda. If we sort of take those two equations and solve for the wavelength, we recover that de Broglie wavelength that you should be familiar with from physics, modern physics, or physics 203 if you took it here, um, that gives us sort of the wavelength of this free particle that, is fundamental for that wave particle duality sort of discussions that you've probably had where quantum mechanical objects have both wave-like and particle-like properties depending on what you're doing with them. Also, if we look at that wave vector and how it related to the energy in our energy eigenvalue equation, that energy can be written in terms of that wave vector, and it ends up being this h bar squared times k squared all over 2m, or if we replace that h bar k with p, that ends up being just p squared over 2m. Again, this is what you would expect classically. P momentum would be mv, so m squared v squared divided by 2m is just the kinetic energy, 1/2 mv squared, which, if there's no potential energy anywhere, as there is with this case, that's exactly what you would expect for the total energy of that system. It also means that although the energy operator and the momentum operator share eigenfunctions, that knowing one, the eigenvalue of one, doesn't necessarily mean you know the eigenvalue of the other, right? If I tell you what the momentum eigenvalue is rather, you can then tell me what the eigenenergy is. But if you tell me the eigenenergy, I don't know what the momentum eigenvalue is, right? Which makes sense, right? There could be in this one-dimensional sort of problem view we're taking of this, if you give me some energy, that could be a particle moving to the right with a given momentum or a particle moving to the left. You don't know which one it would be in this case. And that's an example of what we call degeneracy. If a single energy eigenvalue corresponds to multiple eigenstates of something. And in this case, we have two momentum eigenstates that both share the same eigenenergy. And we're going to see more and more examples of degeneracies as we get further and further along, especially when we expand to like two-dimensional and three-dimensional cases, or if we get to the hydrogen atom, there's a lot of degeneracies in there. All right, so let's put this all back together. If we look at a momentum eigenstate now, well, we have the spatial dependence here is the same as the energy eigenfunction we had. And if we want to know the time dependence, well, we just add that energy dependent phase factor in on that. And if we, bring these exponentials together and sort of do some factoring in the exponents, we get the same sort of wave type equation. In this case, the phase velocity is the momentum divided by 2m, which is actually half of what we would expect classically. This has to do with the fact that this is the phase velocity. It's how fast part of, I guess, the phase value is moving through space. And as we'll see later in the course, the proper velocity we want to use for particles moving through free space is not the phase velocity, but something called the group velocity. So we'll get to that in time. But for now, let's start thinking about, well, what is that A? We still have this unknown constant here. And to solve for what it would be, we need to normalize this wave function, right? And the normalization condition is that the inner product with itself is going to give us 1. And if we do that in the position representation, we get this. And that probability density in here is just the complex conjugate of this. I'm looking at, sorry for the notation, this phi I'm using as the position dependent part of the momentum eigenfunction because the time dependence will just come out and all this. But anyway, the complex conjugate of that position uh, representation of our momentum eigenfunction times the momentum eigenfunction in itself, uh, and you know, plugging in what those position dependent parts of those functions are, we see that probability density for that momentum eigenstate is just a squared. But there's sort of an issue with this, is because if we look at those wave functions, you know, the real and the imaginary part, this momentum eigenfunction, uh, and we're essentially taking those two. If we multiply this probability density together and look at it as a function of x, because we're going to be integrating this over all x, we see that, you know, that is actually a finite value over everywhere in free space, right? The magnitude of that momentum eigenfunction is non-zero everywhere. So if we integrate it from negative infinity to infinity, looks like we're getting infinity, right? You can't really normalize this momentum space eigenfunction. So that's going to be a challenge with how, or at least can be confusing with how we're going to move forward with this. To do that though, let's recall that this is an eigenfunction equation. Momentum is immeasurable. It is Hermitian. Its eigenstates form a bases. They are complete and orthonormal. So if we look at those in our old Dirac-Brocket notation, this is how we would write the properties of those eigenfunctions, right? They're orthogonal. So if I take any two of those eigenfunctions and take the inner product, if they're different, I get 0. If they're the same eigenfunction or eigenstate, we get 1. And then they're complete, so I can expand any state function in terms of that basis. The orthonormality we wrote typically using what's called the Kronecker delta, where if I take the inner product of any two eigenfunctions, I get delta ij, where it's the Kronecker delta, which is equal to 1 if I equals j, and 0 for all other combinations when I does not equal j. In our continuous basis with the momentum eigenfunctions, that becomes an integral from 0 to infinity. And when we take that integral, we get this function, which we call the Dirac delta function. Now, this is a very sort of interesting and weird function. I'm not sure how much of it was covered in perhaps Math 346 or previous courses. So really quickly, just to go through generally how to think about it. First, there is actually a pretty nice Khan Academy video. The link is here, and these are clickable links. I'll try to post the PowerPoints. But the gist is that Dirac delta function is infinite, or it has a value of infinity when the argument equals 0. So if you have delta x minus a is infinite when x equals a, and 0 everywhere else. And it turns out it's infinite in such a way and infinitesimally thin in such a way that if you integrate over that, the area underneath that curve is equal to 1, right? So that means if you have that delta function inside some integral and there's another function there that's a function of x, if you integrate, as long as that a is inside those integrands, the result of that integral is just that function evaluated at that argument, the argument that makes this 0. So this sort of Dirac delta function is how what we use to sort of normalize this wave position representation with our wave functions. Turns out when you do this Dirac normalize our momentum eigenfunction, that constant out front is equal to 1 over the square root of 2 pi times h bar. There's some details on this in Fourier analysis, which we'll get to in a few minutes. And also there's a problem in the textbook, 6.7, that goes through the details of this normalization. But the gist is, with that Dirac delta function, um, we normalize our quote unquote normalize our wave functions so that that constant out front, sorry, is 1 over the square root of 2 pi times h bar. So let's look at the last of those three requirements. That was sort of how we pseudo normalize these momentum eigenfunctions. The other thing that we had with our typical eigenstates for our observables was that they were complete. They formed a complete basis, so you could expand or write any generalized state in terms of those eigenfunctions. So in our momentum representation here, what that would mean is we could write the identity matrix as a sum of those projection operators over all the momentum eigenstates. But since we have a continuous set of eigenstates, we can't really write this in matrix notation because it's an uncountable, enumerable set of eigenstates, but we can change that sum to an integral from negative infinity to infinity over all those momentum eigenstates and use that. Now, the wave function was essentially the similar sort of thing where we were putting the generalized state into those, projecting it into the position sort of bases, and the wave function was essentially this coefficients. They weren't discrete coefficients, but a continuous sort of coefficient as a function of position on that. If we take that and we put in that completeness relation with the momentum space, with the momentum eigenfunctions here, we're still, because this is essentially identity, we're still getting just our writing our wave function in this way. We can bring in the bra and ket inside that integral, and we get these two functions here, right? Or if I rewrite it this way, I have the momentum eigenfunction written in sort of the position basis. This is the wave function for a given momentum eigenstate. And then I have this momentum function, or this phi as a function of p, which is essentially the state function written in terms of the momentum bases, right? So again, because these are different and there's a lot of places where this can kind of lead to confusion, this function here is the wave function or position representation of a given momentum eigenstate. This function is the momentum space wave function. It's the same sort of idea where we have a continuous set of eigenfunctions. Just like with position, x could take on any continuous value from negative infinity to infinity. Likewise with momentum, and if you wanted to know sort of the amplitude or the coefficient in an expansion, we needed a function that described that. This is that function over the variable, over the momentum eigenvalue instead of the position eigenvalues, right? So what we're getting at is we can write that wave function in terms, this way, in terms of our momentum eigenfunctions or eigenbases. And if we plug in what we have, well, we know, we've just shown now that we have our normalization, that our momentum eigenfunctions are written this way, right? And if we bring out that constant term, what we have is our wave function is equal to this, which may look very familiar to many of you. This is the Fourier transform of this momentum space wave function, right? So our position space, or our wave function, is the Fourier transform of our momentum space wave function. And the inverse of that is true. If we take the inverse Fourier transform of our wave function, we get the momentum space wave function. So let's look at what those actually mean, all right? So we're familiar now with our wave function, our position space wave function, right? And we'll have something like this. And if I take that wave function and square it, I'm getting the probability distribution of if I were to measure the position of that particle, what's the particle of it being on some interval, right? So I square this wave function, and if I integrate between, point x equals a and x equals b, get the area under the curve, that's the probability that my measurement of the position would be in that range. This momentum space wave function has a similar sort of thing. It's going to have some functional form. If I take that squared and I integrate, between two given momentum, I'm going to get the probability or the probability that system would be measured with that momentum, right? So again, what we're essentially doing is writing the state of the system or getting the relevant information about the state of the system in either a position basis or a momentum basis, those two continuous variables. And which one we use is really going to be a matter of convenience. We're going to probably focus a lot more on the position space wave function, but yeah, they're just essentially the Fourier and inverse Fourier transform of each other. Um, yeah, so covered quite a bit now with the unbound states uh, today. If you have questions in that, we'll discuss this a lot more in our synchronous sessions, and we'll work on it through the homework and some of the activities.